Hello dear students, welcome to mathematics class. In this class, let us discuss the property of group. So here the property is, if A comma B belongs to G, then the equations Ax equal to B and Ay is equal to B have unique solutions in G. So dear students, we already know that any equation, for example, Ax plus B is equal to C is a linear equation in one variable. So here x is a variable, A, B and C are the constants. So here the solution of this equation means that is the value of x for which the equation is satisfying. So to find the solution of this equation means we need to find the value for x. So here Ax plus B is equal to C is given, then we can write Ax equal to C minus B and then x equal to C minus B divided by A. Now here if you substitute this value in the equation Ax plus B is equal to C, so here A into C minus B divided by A, that is the value for x, plus B is equal to C. So here A and A get cancelled, remaining C minus B plus B is equal to C and B minus B are get cancelled, remaining C is equal to C. That implies that LHS is equal to RHS. Now here it is a linear equation, and for this equation x equal to C minus B divided by A is the solution, means it is the value for x for which the given equation is satisfying. Now here if you replace the value of x, that C minus B by A, by any other value, then the equation will not satisfy. It means that this is the only solution of the equation Ax plus B is equal to C, means the solution is unique for the equation Ax plus B is equal to C, because this is a linear equation. So for linear equation there will be only one solution. So that solution here it is given by C minus B divided by A. Now if you replace the value of x by any other value, then it will not satisfy. So therefore this is the meaning of the given property, that if A comma B belongs to G, then the equations Ax is equal to B and Ay is equal to B have unique solutions, means they are the linear equations in x and y. Anyhow they have the solutions and those solutions must be unique in the group G. Now let us prove this one. Proof: let A comma B belongs to G. It is given that the two elements A and B are in the group G. Now since A belongs to G, it implies that A inverse belongs to G. So here it is given that G is a group, then it has to satisfy the four properties. They are closure law, associative law, identity law and inverse law. So by using inverse law, we can write that if A belongs to G, then A inverse must be in G, right? So therefore A is the element of G, then A inverse is also the element of the group G. Now A inverse belongs to G and B belongs to G. It implies that A inverse B belongs to G. So here this is by using closure law. So here the statement of the closure law is, for all A comma B belongs to G, A star B belongs to G, right? Instead of star we have written the multiplication. Now here A inverse belongs to G and B belongs to G, means these are the two distinct elements of the group G, then by using the closure law we can write that A inverse B belongs to G. Now, given Ax is equal to B. Now, consider this as equation number 1. Given Ax equal to B. This is the equation. Let us assume that let x equal to A inverse into B. Let x equal to A inverse into B is the solution of the equation 1. Let us consider the value of x, which is the solution for the equation Ax is equal to B. Let us consider x equal to A inverse B is the solution of equation 1. Now, if x equal to A inverse into B is the solution of equation 1, then A inverse B must satisfy the equation 1. So, here we are considering that x equal to A inverse B is the solution of equation 1. If it is the solution, then it has to satisfy the equation 1, that only we have written. Now, putting x equal to A inverse into B in Ax is equal to B. So, let us substitute the value for x as A inverse into B in equation 1, that is Ax equal to B. So, here given equation is Ax equal to B, then A into the value of x is A inverse into B, which is equal to B. Now, this can be written as A into A inverse into B is equal to B. So, this is by using associative law, we can write A inverse B as A into A inverse into B. Now, A into A inverse is the identity element. By using inverse law, into B is equal to B, then E into B is equal to what? That is equal to B, which is equal to B. So, therefore, E into B is equal to B because E is the identity element, and then by using the identity law we can say that E into B is equal to B, and here RHS is same, that is B. So, therefore, it implies that LHS equal to RHS means for the value of x, that is A inverse B, we are getting LHS is equal to RHS, means this one is the solution for the equation Ax equal to B. So, it implies that the equation 1 has solution, that is x equal to A inverse into B. So, therefore, now we can conclude that x equal to A inverse B is the solution of equation 1. Now, we need to prove the uniqueness of the solution, because here they have given that they have unique solutions, right. The equations have unique solutions. So, therefore, already now we have proved that x equal to A inverse B is the solution of equation 1, but now we need to prove the uniqueness, means other than A inverse into B, other value will not satisfy the equation 1. Now we shall prove that the solution is unique. The solution is unique. Suppose x equal to C is another solution in G. Let us assume that x equal to C, it is the another value for x which is satisfying the equation 1. Now, put x equal to C in equation 1. So let us substitute x equal to c, because we have assumed that x equal to c is another solution for the equation 1 in the group G. So therefore, we need to substitute the same value for x in equation 1. So therefore, we have Ax equal to b, then by substituting x equal to c, we get a into c is equal to b. Now pre-multiplying equation 1 by pre-multiplying the equation AC is equal to B by A inverse. So here we need to pre-multiply this equation, AC is equal to B. So that is A inverse into AC is equal to A inverse into B. Already we know that what is pre-multiplication, post-multiplication. So now this can be written as A inverse into A is equal to A inverse into B. Here A inverse into A, that is equal to E, and this one is C, which is equal to A inverse into B. Then E into C is equal to C, that is equal to A inverse into B. So here it is the value of C, means we have assumed that x equal to C is the another solution, but finally we are getting C as A inverse into B, means the value of x will not change, means whatever the solution is there, that is equal to A inverse into B. It implies that whatever we assume for the given equation, it will come out to be A inverse into B, means whatever we assume for x, that assumption means the assumed value must be is equal to A inverse into B. Hence the solution of equation Ax is equal to B is unique. Hence the proof. Now we have proved the result for first equation, that is Ax is equal to B. Then we need to prove the same thing for the second equation, that is Ya is equal to B. Now here given, it is a continuation of the same property, given Ya is equal to B, consider this as the second equation. Now let y is equal to BA inverse. Let y is equal to BA inverse is the solution of equation 2. Solution of the equation 2. Now if y is equal to BA inverse is the solution of equation 2, then BA inverse must satisfy the equation 2. So here, as in the previous case, there we have considered A is equal to A inverse into B, but here it is y is equal to BA inverse. Since we have assumed that this is the solution of the equation 2, then that must satisfy the equation 2. Now put y is equal to BA inverse in equation 2. So the given equation is Ya is equal to B, and we need to substitute for y as BA inverse into A is equal to B. Then by using the associative property, we can write the same as B into A inverse into A is equal to B. This is by using associative law. Then by using the inverse property, we can write that A inverse into A as the identity element E. So therefore it is B into E is equal to B. Again B into E is equal to what? B, which is equal to B. So therefore it implies that LHS is equal to RHS, right? So therefore we can conclude that here Y is equal to BA inverse is the solution for the equation 2. So therefore the equation 2 has the solution Y is equal to BA inverse, and then we need to conclude that the solution Y is equal to BA inverse is unique. For that we need to assume again the another solution for Y. We shall prove that the solution of equation 2 is unique. We need to prove the uniqueness of the solution. Assume that Y is equal to C is another solution for equation 2 in the group G. Now put Y is equal to C in equation 2. So therefore the equation 2 is YA is equal to B, then we need to substitute Y is equal to C, then it becomes CA is equal to B, and then we need to find the value for C. For that post multiply the above equation by A inverse. Now we need to post multiply this equation by A inverse, that is CA into C inverse is equal to B into A inverse. Then this one is C into A inverse equal to B A inverse, then it is C into A because of the inverse property, it is equal to B A inverse, C into E is equal to C and it is equal to B A inverse. So here we have assumed the value of C as the different solution, but we are getting the same value what we have assumed previously, that is B into A inverse. So therefore whatever we assume for the given equation, it will come out to be B A inverse. Means here whatever we can assume for the Y equal to C, here the solution will not change. Means here you can consider Y is equal to D is the another solution, then finally you are getting D is equal to B A inverse only. So therefore there is no other solution than this B A inverse. Hence the solution of equation 2 is unique. Hence the proof. So therefore here we have proved that for both the equations Ax equal to B and Ay is equal to B, we have solutions in the group G and they are unique.